Dear ladies and gentlemen, welcome to our Burckhardt Compression Tech Exchange. We are very happy that you take your time today and join our live webinar. My name is Daniela Daron, and I will guide you through the presentation today. Before we start, I would like to give you some information. The session will be recorded, and there is the possibility to ask questions in the Q&A box. You find it either on the bottom or on the top of the navigation bar. We will answer the question at the end of the session. Due to time restrictions, we may not be able to answer all the questions, but we will get back to you personally if there will be any questions we couldn't answer. And of course, all of your microphones are muted. I just saw that someone raised the hand, so please place your question in the Q&A box. So in our Tech Exchange webinars, we give you technology insights of reciprocating compressors. And today we will look into the topic reliability. How do we eliminate bad actors? And the three key takeaways are the deeper understanding of the importance of a reliability process, the identification of failures and failure modes, and best practice on root cause analysis. And the two expert speakers today are Jonas Gomez. He's a technical director at Burckhardt Compression, and he has over 16 years of experience in the compressor business. And then we are very happy to have also Vitaly with us. He's a sales manager, operate and revamp projects, and he has over 10 years of experience in the compressor business. And with this, I would like to hand over to Jonas.
Thank you, Daniela. Good morning, good afternoon, good evening. My name is Jonas Gomez. It's a pleasure to be with you here on this Tech Exchange. So let's start our topic today. It's reciprocating compressors and reliability. Here you see a typical arrangement of a reciprocating compressor gas system. And well, you may see here different components, different equipments, and let's go shortly through them. So you can see here the compressor is placed in the middle, responsible for the compression of the gas. Additionally, you have probably a driver, can be an e-motor, can be a steam turbine, responsible of providing the torque on the compressor. As well as we have the loop system. Other equipments that you may see here are heat exchangers and pipings and instrumentation. So the reliability of this complete compressor gas system is depending on the performance and availability, reliability of all these systems together, okay? And if they are failing, probably you can have some unexpected shutdown or any event. So the question about reliability is, how do you deal with the failures of these equipments? If you answer this question, you're probably answering how you are dealing or how you are performing the reliability. Diving a little bit inside of the machine, we can see here a nice drawing about that, and we see some main components, some critical components of the compressor itself. So you see, for example, the compressor valves. You can see also some piston and guide rings responsible for effectively sealing the piston inside of the cylinder. Also, a critical equipment component can be the packings and the piston rods. So again, let's revert to reliability. So if these components are failing, how do you treat these failures? Okay, how do you investigate them? So to avoid repeated failures, investigation are strongly recommended to understand why these components are failing, the components of the compressor. And you should learn, or learning from these failures is a very good best practice, okay? So if you have a failure, or if you have an expected shutdown of the machine, maybe you have an accident or loss of production, or even an environmental impact related to the compressor. One is the best practice of investigating that. So first, try to identify the disciplines, the dimensions that may be a cause of this failure. So one, for example, is operation, production. So the process itself can affect and be a cause of that. So try to identify these causes. Another main discipline is the maintenance. So how the maintenance was done, okay, the process of doing maintenance. The design itself from the component or from the compressor can also be a cause of this failure. Materials, they play an important role on the performance of the machine and should be correlated if the failure. Is there any external factor? For example, weather conditions may also affect the compressor, and any other discipline. So try to inspire yourself, identify these main disciplines, and take the note of all these possible causes, okay? Once you go deeper and you go into this investigation and you identify the probable root causes of this failure, okay? So here we identify in the red arrows just a selection of those. List them, because then you need now to eliminate, you need to eliminate these causes of the failures. So how you eliminate them? You should discuss, contact your OEM, contact the specialist, try to define, try to propose a solution, maybe a small change or a minor change on the materials, on the working process, or eventually in the process parameters. Once you implement these modifications, you're going to eliminate the causes and eliminate the impact of these causes, and for sure, increasing the performance of your machine. Now I'm going to hand over to Vitaly Tatarinov, where he's going to present a nice case of an investigation of a failure on a South African petrochemical plant. Thank you very much. Vitaly.
Thank you, Jonas. Good day, dear ladies and gentlemen. So let me offer an example of failure investigation on a reciprocating compressor. And here the conversation goes about vertical machine, which you can see on a slide, with a moderate speed, relatively short stroke. It's compressing ethylene in a downstream segment, petrochemical and refining plant, and it's compressing ethylene in a dry running mode. So pressure range and the temperature range are moderate, very common for this kind of process. And a failure and unreliable behavior here is of sealing systems. That is a pressure packing and piston rings in cylinders of both stages. So basically, to begin with, we have to identify a problem. Let's say, what exactly shows what are exactly the description of unreliable behavior. And here, for this particular compressor, for unreliable behavior is responsible a sealing system with a very short lifetime operation. So as short as 3 months of operating lifetime has been reported for piston rod packing sealing elements and piston rings. Another important thing is that high leakages have been observed during operation in the compressor. Last but not least, and also noticeable effect is a wear of a contour surface part. In this case, piston rod surface quickly lost roughness and get polished after a short time in operation. So this is basically a general description of the problem. However, as a next step, we would need to go deeper and need to collect facts about a problem. So in this case, we went with a detailed site survey with an inspection on site for a compressor, which consisted of several main pillars. One of them was a measurement, so the measurement inspection on a compressor parts which are involved in unreliable behavior. That is liner condition, rod condition with measurements, as well as some characteristics, parameters of the contour surface like a roughness. So all these things have been measured and reported for future failure investigation. Next important step is basically visual inspection. This includes walk around check around working machine, looking and observing parameters, as well as inspection when compressor is disassembled, so we have an access to the failing parts. Third one is maintenance documentation. And in this case, it provided first a valuable fixed source of frequency of the failures which have been observed, maintenance interventions which were related to the failure, as well as a record of design changes which have been introduced to machine, which actually contributed significantly to analysis of the failure causes. Last but not least, it's a meeting and discussion with technical specialists on site. This involved maintenance and mechanical crew of compressor operator as well as process specialists. This is absolutely necessary to understand an operating and maintenance context of compressor, because it forms a separate categories of possible failures and can be shown later on. So this time is really needed to get an accurate and complete problem description and collect the data about failure. Once it is done, we basically can go with root cause analysis. And the first step is to identify possible causes. And this can be done in several ways. In this particular case of failure investigation, we have used Ishikawa or a fishbone diagram. And basically, the idea is having a symptoms or effects picture that lifetime is short, leakages are high, and all the effects which we collected during problem description. We can look for causes which bring that or another effect. And for this, we have these major categories which are listed here on the left from the symptoms. And we can expand them by asking question why and going in a more detailed level for each of those categories. So if you speak about sealing material of a piston rings or pressure packing sealing elements, we can look in material whether stiffness of this material is not high enough, if it allows, let's say, sufficient adaptability of the rings when wear comes in. If hardness of this material is not too high, and if it does not or does cause the accelerated wear of a contour surface. If creeping resistance or chemical resistance are sufficient and are not responsible for failures which we observe. If you go to the sealing element design itself, is quantity of the rings optimal for this pressure range, for this application, for this molecular weight of the gas? Is there a function principle, how the ring behaves during operation, how it responds to wear? Is this wear compensated? This is also important to consider. Next important thing is for dry running systems, especially this is crucial, is a condition of a counterpart surface, whether its typological characteristics are in line with application, that is a roughness of piston rod or liner surface, that is a treatment composition of the running surface, which is assigned to the parts. It's geometrical data, tolerances, and then the dimensions. All these parts are forming typological behavior of the system. So does the material of the ring actually fits to the counterpart treatment and condition? Compressor design. If compressor speed and the mean piston speed are actually fine or not too high for the application selected. Compressor medium, also important source of potential failures, whether the gas composition, impurities, humidities are affecting the lifetime of the rings. Two important factors here to mention is also operating procedures, whether the variation of parameters versus design is high or not, and maintenance practices. That is guidelines which are used during assembly, testing, storage of components. So basically, having expanded this tree and listing all possible causes, and it's important to say, we really try to list all possible causes which can potentially lead to observed picture of a failure. We do not try to eliminate these causes now or challenge them in a hard way. This should be done on the next step. So once we collected this tree, we constructed this fishbone, we can start with identification of probable causes. And for that, one by one, we needed to eliminate the causes which are unlikely causing this failure behavior based on the gathering data. So here, having this tree, we start to eliminate causes based on things that they do not explain observed effects. They do not provide a mechanism which can explain observed picture. And once it's done, once we cross out one by one all these unlikely causes, we remain with something which is left, which is tested if it describes, if this hypothesis describes a behavior which we see. And it is basically important in this point to have an explanation. On one side, does proposed causes explain all observed facts? And on the other side, it's important to say that these causes does not offer some absent effects which are not have seen on a machine, but would be definitely come as a result. So challenge these causes and really try to make a link from them to the effects which you have seen during the problem statement and problem description. And in this case, we have left out with a material condition or specification and counterpart condition and the design parameters. And let's say in this case, we need to ask, so does it explain all symptoms which we have seen? And we can say yes, because high stiffness of the sealant material does not allow good adaptability of the rings when it's worn. One can observe high leakages in operation. Counterpart polishing is a result of higher abrasiveness of a ring material, which in this case was a P grade, which is definitely not the best application for a moderate pressures and a dry running sealant design as in this case. Altogether, this mismatch of counterpart and sealant element, they were responsible for a short lifetime of operation because matching of tribological system was not definitely the optimal one. Next, once we have listed these causes, we can go with improvements and introduce actions on a machine. So in this case, of course, first was change a material of sealant elements. Instead of P grade, not suitable for this operating range, we selected a polymer blend material, which allows much higher adaptability. It's much less abrasive to the contour surface, basically causing on one side a good lifetime, on the second sealant characteristics of the system. Another part was contour surfaces, so piston rod coating was updated, its roughness has been changed, as well as our cylinder liner roughness has been changed in order to have a proper behavior of sealing system for a dry running application. By saying that, we mean that roughness should be in a specific range to form basically so-called transfer film of polymer material on a counterpart and switch mode of, let's say, friction from a polymer to metal to polymer-polymer one, which definitely is much favorable for a dry running application and is desirable. So with this complex of measures, we could achieve a much better performance, and it will be shown on the next slide. But before that, I would like summarize a process which we have applied in this particular case. So we started with a problem statement, with understanding what actually is wrong, why we consider system unreliable. Then, as a next step, was a problem description with following site inspection to collect as much as possible data for basically checking the causes which we would identify if they are probable, if they are likely, happens the symptoms, the observed picture on the next step. Once we have listed these responsible problems and failures, we need to go and assign appropriate countermeasures. Once they are implemented, they of course need to be followed up. So what has been done in this case, and the result was actually proven approach, because from 3 months in operation, now the sealing system is over 24 months in operation. So it allowed multiple impulses in a lifetime of the ring. And important effect of that was also that in operation now compressor has original capacity recovered. So it does not decrease with time and operation as one could expect because of poor sealing performance of pressure packing, but namely piston rings. So for that, basically, this is a summary of applied approach. And of course, in general, all improvements on a reciprocating compressors, they should be done on the basis of failure investigation. Once bad actors are identified, failure root cause analysis of the failure needs to be done with identification of causes, because only understanding this process, one can actually get inside and come up with corrective actions. Because in the end, sealing system performance is, in this case, defining performance of overall compressor, and compressor was defining performance of the plant, its reliability and availability. So with this, I thank you for attention, and I give word to Jonas for a Q&A session.
Okay, Vitaly, thank you very much for your great explanation about this case in South Africa. So let's have a look on the question box here. Vitaly, I think the first one is for you. How important was the collaboration between you and the customer's process team during this investigation, during specific case here?
Yes, I would say at least as important as cooperation with mechanical and maintenance specialists, because compressed gas is a, let's say, very important source of potential behavior or causes of sealing systems. So impurities which are coming in a gas, process variation, all these parameters must be considered during failure investigations. Therefore, it was very important discussion which we had in this case to eliminate possible causes.
Thank you, Vitaly. There's another question here. Maybe I can try to answer. What are the risks of not applying the reliability process for investigation of failure? So if I understand here is like, what are the risks of not doing a proper RCA or investigation this failure? Look, let's revert to the case that Vitaly just explained it. He showed the Ishikawa diagram. He showed this fishbone with several points that could be the cause of this failure. So when you are doing this RCA or this investigation, you are also learning a lot. Okay, you are learning your machine, you are learning your process. So that means you can avoid in the future repeated failures again, because you learn that you can keep this information in your books. You can share this inside of your plant team, your maintenance team, your process team, and improve the situation. Another risk that I see is even higher. Okay, answering the question is, if you don't perform an RCA and if you just believe on a specific cause, if you are sure about the cause without doing a proper RCA, you fall in a risk of implementing some actions that are not effectively eliminating the causes, and consequently you can have this repeated failure again. Okay, so answering here the question is like, you don't learn and you can mislead the decisions, mislead the improvements, not eliminating the causes. Okay, so I see here other questions coming. Vitaly, for this specific case, how long it took to perform this investigation, this RCA you just presented now?
I would say active phase was fairly short. It was approximately 2 days. So it was active discussions on site, joined together with site inspection and active development of actions. I would say identified probable causes. We had approximately 2 days after investigation has started. Of course, with some design checks had to follow, but that was not that long. Yeah.
Okay, thank you, Vitaly. I have another question here. Were these changes applied to the whole fleet, other compressors types as well? Maybe I can answer this question. So I say yes. In this case, customer had more than one compressor, so both compressors were were facing the similar failure mode or the similar impacts. So once the first machine was modified, the second machine as well was receiving this improvement. Okay, so and of course this what I mentioned before, this learning about the process is applied in other compressors. I have another question here for you, Vitaly. Can Burckhardt perform failure investigation for other OEMs or only for Burckhardt machine?
But basically, as long as we speak about reciprocating compressors, yes, we definitely can do that.
Okay, thank you. Another question here. I have a monitoring system in my compressor and I use it for machine protection. How can I use the monitoring data for the failure investigation? Can you answer that, Vitaly?
Yes, basically a monitoring system is a valuable source of information, of course, because it allows to look inside of compressor in many aspects. When we speak about cylinder pressure measurement, indication of compression chambers, now monitoring systems can make a crank angle dependent vibration overview and analysis. So all these things are important contributors of input data for analysis. Of course, that does not automatically substitute any logical or analytical procedure by a fishbone, by fault tree analysis, whatever is applied, but it's a valuable source of information.
Thank you, Vitaly. There's another question coming also related to monitoring. So I assume the question was also answered. I'm just going to read the question. Do you consider data-driven monitoring to improve time efficiency on RCA? So yes, Vitaly just answered, just contributing on that. So when you have the monitoring data, you can really, depending on the failure you observe, you have a quite precise timeline on this machine behavior, on the machine vibration, on the process. So you can correlate the data of the machine from your monitoring system and correlate with that with the process data and looking on really on a timeline and increasing the efficiency or increasing the time or reducing the time for the investigation, as well the probability of identifying the causes and consequently eliminating them. Okay. I think there's one more. Would conversion from non-loop to loop also improve the lifetime of the piston rings? That's a good question. Maybe I can try to answer, Vitaly. Let me try to give some words, and then Vitaly, I count with you. So yes, if you are having a dry running machine and you are facing a short lifetime, frequently, if you add a lubrication there, you can probably increase the lifetime of these components, or the piston rings and the packing rings. The limitation is are you allowed to introduce these lubricants inside of the process? If it's not, and in most of the common cases, you are not allowed to introduce lubricants inside of the process. So that is a good question. So it depends. If you're allowed, then yes. If you're not allowed, then you need to deal with materials and other aspects. I think we have other questions here. Thank you very much for the questions. I'm going to hand back to Daniela to close the session.
Thank you very much, Jonas, for guiding us through the Q&A, and also thank you very much to Vitaly for your explanations and interesting presentation. Yes, we are already at the end. If you'd like to stay informed about our TechXchange, and if you haven't yet registered to our distribution list, please feel free to do so on our website, and you will stay informed also in the future. With this, we're coming to an end. The recording will be provided to you by a separate email, and there will be also a survey link in it. So we really would like your feedback to learn and to make also the upcoming TechXchange webinars interesting for you. Again, thank you very much for your time and hope to see you soon. Bye-bye.